Hi, Mick McQuaid here. I'd like to demystify the process of making maps from documents or matrices of numbers. So I'd like to help you make your own maps from documents or matrices of numbers, and I'd like to explain what I mean by that and how to do it. But first, I'd like to give you a little bit of background. So the background is about information overload. So messages compete for your attention all the time, and they're important messages. You can't read them all. There's just too much, and all of it is important. It's information overload. So how can you stay in touch with it all? Especially this one, circuses face clown shortage because top talent prospects are increasingly choosing careers in politics. These messages are really important, but we need to reduce somehow the need to read every little bit of information that comes across to us. So the goal is to create a map of this text. And by a map, I mean a picture of the similarity between pieces of text, the distances between pieces of text. And let me make this a little bit more concrete by showing you a map that I made of a bunch of websites of disability services offices on college campuses. So this is 39 disability services websites. 36 universities are represented. 3 of them have their websites divided into 2 different websites, sometimes kind of unrelated to each other, or only loosely related to each other. And so what I want to do with this talk is show you how to create this map or a map like it. And it is based on how similar these websites are according to their textual content. Now, why might you want to do this? It's because you want to do things like, in this example, notice Washington University of St. Louis and Carnegie Mellon have very similar websites. So I would look at them together. If I have to analyze these websites, I would look at them in clumps, in groups, in clusters, rather than just one at a time and then saying, hey, didn't I see that before? So here's an overview of the process, and you'll have to forgive me for using some very old memes here. I just don't have time to get out to Reddit and every year and find out what the current memes are. So the process is just data prepping, extracting tokens from documents. Tokens and documents are terminology from the information retrieval world, and they just mean, in this case, words and pairs of words on the one hand, and websites on the other hand, or web pages. And then I convert the tokens to numbers. So I convert each word into a number, and that gives me a token times document matrix, where each row is a document, or each row is a website, and each column is a token, a word or a pair of words. And I apply a dimension reduction algorithm that gives me a document times 2 matrix instead of a document times the total number of terms matrix. So a 2-dimensional matrix is something that I can plot on a flat surface. And so I plot the documents in 2 dimensions, which is what you saw in that previous picture of a map. Now we start with data prepping, and 70% of data science is data prepping, and the other 30% is complaining about data prepping. So I have to tell you a little bit about data prepping, which is, of course, a little bit tedious, but it's necessary. So the researchers in this case kept a spreadsheet of URLs of the websites of these disability services offices that they were studying. So I copy that spreadsheet to a TSV file, that's a tab separated values file, And that's just a list of URLs, basically, a list of colleges in one column, and then a tab, and then a list of the URLs in the next column. And then I run two Python scripts. First, I run a Python script called dump sites on that file that gives me a set of files, one per website. And I use a text-only browser, in fact, the oldest of all contemporary browsers, Lynx, to dump those sites into text files. So the output of that is a text file per website containing all the text from the website. Then I run a second Python script called stringify that converts every file to one single string. So I now have a table which is called blah, because I couldn't think of a better name, and it contains a website per row. So each website is just one long string in each row. So this file is only 39 rows long, but it's very wide. And here are the contents of the two Python scripts. This is the first one. And to run it, you don't need to really know Python. You just need to know that you have a file called sites.tsv in the current folder. And then you also need to know that you have Lynx, this text-based web browser that I mentioned, on your computer, and a program called iconv, I-C-O-N-V, on your computer. And the reason for that second program, iconv, is that in my case, some of the websites that I was trying to dump were not encoded in a standard format. So there's a sort of standard character encoding called Unicode that you might be familiar with, that most websites are encoded in. Well, a few websites adhere to an older kind of coding, in this case Latin 1, and sometimes in other cases another strange encoding. And so I converted all the Latin 1, I think it was the University of Southern California, or somebody had Latin 1 website. So I convert anything that's Latin 1 into UTF-8. And that gives me a file that has as its name the name of the URL, which in the United States is guaranteed to be unique. So they're all edu websites. So you know, Stanford is the base name of the URL for Stanford's website, RIT for RIT, WUSTL for Washington University of St. Louis, and so on. Then the other Python script is this. This converts the text files into strings, so it takes a list of arguments, which are all the text files in the current folder, and just reads them in, puts in the file name as the first word in the output file, and then a tab, and then all the text that was in that file, and replaces all new lines with spaces, so they all go on, so each website goes on one line, and replaces all tabs with spaces, so that the only tab in there is the tab separating the name of the college from the text in the website. Now the whole rest of the process is done in R. So you need both Python and R to run this process. And base R has some capabilities, but mostly R works with packages. And these packages are pre-programmed scripts so that you don't have to do programming. You can just run these scripts and they sort of do the programming for you. And they're stored in a library and brought into the current environment. So those are R jargon terms, like library is the collection of all packages. So for example, I have 408 packages in my library, and I don't want their code getting all mixed up in the environment. I only want to bring the environment, which is where I'm actually running code, to have what I absolutely need. So I use the library function or the require function to bring the packages into the current environment. And here you see a list of all the packages that I brought into the current environment to do this process. And a lot of them are bundled together in a meta package called the tidyverse. So there are actually two popular ways of working in R. One is to use base R, and the other, and a lot of add-ons, and the other is to use the tidyverse. And so I teach in my classes the tidyverse approach, and I use it in here. And the other packages here are just text mining packages for the most part, or utility packages. Now you may be wondering about the lambda symbol and the curly braces at the top, which are not part of the code. This entire process, both the Python and the R code, is all encapsulated in one file called an R Markdown file. And this is a version of Markdown that's intended to be both understood by program interpreters like R and Python, and also by text engines like LaTeX that convert it into a document. So this is an example of literate programming and reproducible research. So you have what you have in this one file is both a document and the code that can be both compiled as code and run as code, and also compiled and viewed as a document. And the lambda symbol and the M dash at the bottom delimit a code chunk in the document. So the way the document works is there's a chunk of code, and then there's some documentation, and then another chunk of code, and then more documentation, and so on. And I'll show you that now. So for example, here are two chunks and some documentation in between. And a key difference between this and just commenting your code is that this documentation isn't just sentences like what I show here, prepare the data by making it lowercase, etc. It could also be equations or diagrams or videos or whatever you want to put in it. So, and the two, oh, and I see a mistake in one of the code chunks here. So it says at the top that I'm going to read in blah 2, and actually I'm going to read in blah. I was just experimenting with blah 2 at some point. So that just reads in this file that I mentioned before, reads it into R, and then the names of the colleges are actually the names of the colleges followed by .txt, so I have to remove that. So line 3 there is just removing the .txt from the names of the colleges. And then below there where it says prep data on line 8, that's just a function, the creation of a function that makes the text lowercase, removes non-alphanumeric symbols, and collapses multiple spaces. Now I'm going to skip much of the document, much of the file that this code is in, which by the way I'm going to share at the end of this presentation. I'm going to share that file with you. I'm going to skip quite a lot of it because it was just playing with the data. So it's in there and you can look at it if you want to play with this particular data set. It's also possibly useful when you're doing your own data set to see different ways that you can play with the data. But I'm going to skip that and just show a documentation chunk. Well, here's a code chunk first and a documentation chunk. The code chunk here is just creating a word cloud from the content, and the documentation chunk are just some notes that I took on what I found when I was playing with the data. So these are interesting things that you just want to include in along with the code to say what you found, and that you can come back to later in case it turns out to be relevant to the paper you're writing. So for example, I found that a couple of the schools had a lot of mentions of themselves, and then other schools had very few mentions of themselves on their websites. One website encourages you to visit its new website but has no links to its new website. One university has a 5-step process to make you eligible for accommodations. Another university has an 11-step process. So I found that very interesting. Two of the universities use the abbreviation DSP all over the place. And so from the point of view of textual similarity, these two look very similar, so I actually removed the expression DSP from the vocabulary of the process, so they wouldn't look the same for what I considered a spurious reason. So the next phase of the process after playing with the data is to do some text mining. And I found the text miner package in R to be ideal for that. There are numerous text mining packages, but experience has shown me that text miner is the best. And text miner follows really mainly a two-step process. First, I create a matrix of the out of the documents and the terms or tokens, and that's what's seen here, the create DTM function. And you can see the defaults mostly for that function, which I left in to help me understand you know, just what the defaults are without having to think about it or go back to the manual. So a lot of and some of these defaults are kind of unimportant. For example, stop words. There's a lot of research that shows that stop wording is not a very effective tool in text processing, and stop wording is therefore kind of old-fashioned, and it's included here by default, so I included it, but it's not really that helpful. Ngram window is a very informative default that tells how long the phrases are that I'm going to include. So I include phrases that consist of one word or phrases that consist of two words. So that's on line 4 where it says minimum and maximum n-gram length. And n-gram is just a series of n words that co-occur a lot together. And then near the bottom is a line that I added after considerable iteration. So I did this process, and then I found that I had left in a lot. So taking out the stop words doesn't take out stop words like HTTP, index.html, and so on. And so I went back and later removed a bunch of these, which are highlighted in green there on line 12. And I didn't take enough out. As a matter of fact, you'll see later in this presentation that I needed to take more out. I actually went back several times, but I didn't go back often enough. Okay, so the result of that create DTM function is this matrix, this token by document matrix, and it started out being 39 times about 2,500 or so. And gradually I removed terms. So for example, I removed any term that occurred less than 3 times in the corpus, in the body of documents, and I removed any term that occurs in every document except the word students. So taking off both ends, the words that occur too frequently and the words that don't occur frequently enough, I end up with the salient terms, the terms that distinguish one website from another. And I examine them iteratively. I go back over this again and again to arrive at those numbers. And I'm able to eliminate columns that make no sense, like index.html, which is ubiquitous. And now the only token that appears in all documents is students, as I said. Okay, and here's an example of some of the output. So the top 2 lines tell the size of the output the last time that I ran it. The next 3 lines show the first 6 columns of the matrix. The columns are the terms that appear in the matrix. So those are words or pairs of words. And the rows are the names of the universities. So down below you can see a snippet of the matrix starting with the first 6 rows there: ASU, Berkeley, Brown, Caltech, Carnegie Mellon, and Columbia. And if you look back up at the terms, you can tell that accessibility_campus does not appear in any of those 6. So that first column of dots means that nothing appeared in none of those that term didn't appear in any of those documents. But accommodation process occurred once each in 3 of the documents, Berkeley, Brown, and Caltech. And the third one, accommodations _temporary, appears in Caltech, and so on with the rest of them and the rest of the matrix. Here's some more output. So this is just the term frequency, document frequency, and inverse document frequency for disability services, current students, and so on. And so you see that disability services occurred 151 times in a total of 15 of the websites. And then I do this, the second part of this text mining process is creating a TF-IDF table, that is term frequency times inverse document frequency matrix of that. And that's lines 7 and 8 that create that matrix. Then using that matrix, I find the cosine similarity between the documents. So this is a measure of the difference or the distance, how close documents are, and it's measured in terms of similarity, so that the largest number would be the most similar. Then the last 2 lines, 11 and 12, convert that similarity into distance. And that, oh, and let me say one thing about cosine similarity. So you can just take those 2 lines out, 9 and 10, and substitute a different form of similarity instead. That's, and just compute a different form of similarity. So for example, the reason that I wanted to mention this was because Kerr had a doctoral student who did Jacquard similarity in her doctoral work, and all she would have to do in this case to do that would be to take out the lines 9 and 10 and put the definition of Jacquard similarity in there instead. So you can use any one you want. I just used cosine similarity because it's the most popular, it's the most heavily researched form of similarity, not any special reason. And then the lines 11 and 12 are the conversion of the similarity into distance by taking 1 minus the similarity. That's where it says 1 minus C-sim, and creating that as a distance measure. So that creates this new matrix. So CDIST is a matrix of the distances between the university websites. So the last phase of the process, which used to be the hardest phase of the process, when I was a doctoral student, I had to do this part in C and implement individual algorithms for mapping myself. It was a real drag, and we had to walk uphill both ways to school in those days too. But now it's so simple. Let me give you an idea of what not really the process, but just what the algorithm has to do, what it's trying to accomplish. So I'm taking 4 cities here, and 2 of these cities are in the mountains, and 2 of them are in a valley. So in 3 dimensions, this distance map doesn't make sense. This distance map here that you see in 2 dimensions is an approximation of the 3-dimensional view of these cities. So if we take a look at these cities in 3 dimensions, we see that Flagstaff and Tucson are in the mountains, and Phoenix and Albuquerque are in valleys. And so if we want to fit a 2-dimensional plane to it, we have to approximate. And that's what those little yellow and white lines are approximations of the 3 dimensions to 2 dimensions. And what I'm doing with this distance map is reducing from 1133 dimensions down to 2 dimensions. So I can't visualize that, so that's why I'm showing you this example of a city distance map to give you an intuition for what it's like. The principle is exactly the same, it's just not easy to visualize, 1133 dimensions. And the code to do that is just line 2 on this slide, where it says t-SNE cosine gets t-SNE c-dist perplexity equals 5. The t-SNE algorithm is completely encapsulated in the t-SNE function. And what does t-SNE stand for? I've forgotten what t-SNE stands for. You can find plenty of websites about it to find out what it's an abbreviation for. But the S in it stands for stochastic. And so there is a stochastic element to this. So when you run this algorithm several times, you get potentially slightly different maps. And so it's a good idea to run this algorithm repeatedly and see what patterns emerge that are kind of stable and enduring. So that object, t-SNE cosine, is the t-SNE dimension reduction based on cosine similarity. That is a 2 by 39 matrix. And I plot it. The next line is I plot it, and I'm going to show you that plot in a minute. And then I check the type of it, and the type of it is a matrix. So that's not good for the kind of plotting I want to do. So then on line 5, I convert it to a data frame. And on line 6, I give that data frame column names. So a data frame you can think of as kind of like a spreadsheet. And so this spreadsheet has 2 columns, and one of them has the label X and the other one has the label Y. And they're just X and Y coordinates for the colleges. So on line 7, I plot it in a more sophisticated way. But that more sophisticated way still isn't ideal. So lines 8 through 19, the whole rest of it, is a plot that takes away a bunch of the baloney that's in that plot on line 7 and reduces it down to what we want to see. So let me show you those 3 plots to show you what I mean. So this first plot is just the raw plot of the t-SNE output. Each circle here represents a college. This plot looks a little better because the colleges are now labeled, but it has 2 drawbacks. One of them is a small drawback, which is that some of the labels are obscured. For example, you can't really see Cornell hidden behind UMBC, and you can't really see MIT hidden behind UMich. And a couple of the other ones are somewhat obscured. But the bigger problem is the depiction of the X and Y axes. So the X and Y axes have no interpretation in this kind of dimension reduction exercise. And that's kind of hard for people to wrap their heads around. People want to think that, on the left of the x-axis means less of some quantity, and on the right of the x-axis means more of some quantity. And that's not really the case here. The x-axis is simply the dimension of greatest variability in the data. And the algorithm has nothing to say about what constitutes that dimension. You would actually have to painstakingly examine the tokens in the documents to figure out what the dimension of greatest variability is in some sort of meaningful sense. So I want to get rid of the X and Y axes. And so all that other code just gets rid of all the decorations and all that stuff and leaves us with this map, which is the map I showed you at the very beginning. So this is really the end of the process. However, after the last phase of the process, I did a few other things. So I have all these distances laying around. So one of the things that occurs to me to do with these distances is to cluster the websites. So it's not as interesting to me as a map, and it's not as useful to me as a map. I can actually use that map to figure out which websites to analyze together, which websites to read together, and which ones I might be able to just gloss through, skip through. But the clustering depiction gives me some of that same information. So this hierarchical clustering process starts by putting every single website in its own cluster, and then it gradually adds more of them together until they're all in one big cluster that contains everything. And this dendrogram, this picture is called a dendrogram, is a depiction of that process. And so that you read it from the bottom to the top. So the bottom, the beginning of this process, is where Cornell and UMBC come together. You can see that the two little lines that extend to them are lower on the diagram than any other lines in the diagram. And you can also see that the next thing that happens is that ASU and Rice are put together in a cluster, and the next thing after that is UNR is added to that cluster, and then the next thing after that is either University of Kentucky is added to that cluster, or Carnegie Mellon and Wustl form a cluster. I'm not sure. I would have to hold a ruler against the dendrogram to tell which one comes next, and so on until they're all in one cluster. So you can cut off this dendrogram at any level that gives you anywhere from n to 1 clusters. And I cut it off where I got 8 clusters here, and those 8 clusters are outlined here. And I want to show you some other things that I did with those 8 clusters. So I made word clouds of each of the clusters to get an idea of how the clusters differ from each other, how the emphases of those websites differ from each other. So here's an example, if it'll ever show up, there it is, of cluster number 2. So the thing that was most salient in cluster number 2 was the word health. And after that, the words drop and services, and after that, no, I guess services was second and drop and hours are third. And you can see that I have that spurious HTTPS accessibility in there. That's one of the things that I should go back and remove from the, and services HTTPS is another thing that I should remove from the analysis. And let me show you one other cluster. This is the cluster number 3. This is the word cloud for cluster number 3, which has accessibility as its main word, and email, life support, and campus. I guess email is second, and then life support. I mean, life and support are two different things. It's not like a life support system. They're two separate things. If they were together, there would be an underscore between them. And campus. Okay, and then the very last thing that I did is map the scores. So the researchers, in examining each website carefully, assigned a score to each website on a couple dozen characteristics of how easy it would be for a student to use this website to accomplish certain tasks, like finding documentation, undergoing the accommodation process, and different things like that. So that score sheet is a spreadsheet that is a matrix of numbers, and I can map any matrix of numbers to see how similar the objects that are represented are. And so I just did that. It's exactly like the previous process. I have the code already available to me. I just take out the first step of the process of converting the words to numbers. The words have already, in a sense, been converted into numbers here. And what I find out from here is that Caltech, Berkeley, and MIT are outliers in this score sheet. And I might not be able to tell that from looking at the score sheet. If I look directly at that spreadsheet, I can tell the row totals and the column totals. So I could tell, for example, which two websites had the highest score, and I could say that they're similar in the sense of both having a high score, but nobody had a high score on everything. So two websites might have the same score, and their scores come from different characteristics, from doing well on different characteristics. Now, another way I can look at this spreadsheet is through a biplot. So I did that as well, and a biplot plots both the rows, which are in black here, and the columns, which are in red. So the columns appear as vectors here, and the columns are the characteristics that they were being evaluated on. They're academic, online portal, documentation guidelines, career services, and each website got a score from 0 to 2 on each of these characteristics. And so some of them clumped together on this, like UW and UNCG, Stanford and Harvard, clumped together on this. And almost all of the vectors point in roughly the same direction. They all sort of point to the right, except for documentation guidelines. So documentation guidelines was an outlier. The way that websites scored on documentation guidelines differed substantially from the way they scored on other measures. Okay, so that's it. All I want to do is ask you to visit these URLs to get the code and the rendered output. So as I mentioned before, this was an exercise in literate programming and reproducible research. So if you have this file analyze.rmd and the list of websites, which I'm not giving you, you could actually reproduce everything that I did precisely. But I intended it for you to use your own list of websites or your own list of documents, whatever it is that you want to analyze. So that's why I'm giving you the code. And then the analyze.pdf is the literate version of it. That is the rendered version. It has all the word clouds, all the maps, everything, all the output of the program, and the input is rendered nicely so that it's easily readable with like section headings and stuff. Okay, so that's all that I have to say. I would gladly entertain questions if I were there, and I may be there. My class overlaps with the CARE meeting, so I may not be there, in which case I'm happy to entertain questions later if you want to write them down or something, or email me or whatever. But thank you very much for your attention.